All right, so I'm Jason Harrelson. Can everyone hear me all right? I know it's really packed, so a lot of you had to sit in the back. I apologize you couldn't be closer, but it's probably a good idea because I tend to play too loud. I am Jason Harrelson with Harrelson Trumpets. Since it's a small crowd, I imagine most of you have an idea what's going on today. But what I'd like to talk about is standing wave efficiency, which is kind of the physics, acoustic side of music and musical instruments. And I'd also like to incorporate the efficiency of airflow in terms of how it goes through your instrument, through your mouthpiece, and then tie that together with your embouchure. I don't normally put all those together, but I did that because I've actually had quite a few questions today and in recent weeks where people are asking how all that fits together. And that's really my focus, is working with people and helping them solve problems by putting the human aspect together with the mouthpiece, which tends to be between the manufacturer of the horn and the person, along with the horn. So there really are, I'm kind of looking at three components of efficiency today: the human, or the way that you play; the mouthpiece, which a lot of times you buy separate and you don't get with your instrument, and then the instruments. I think it's probably best to just talk about the instruments first, and acoustics and the physics of acoustics, and how that works. If anyone remembers from your physics classes, we have waves, which look like waves on water, or like the waves when you skip a rope. Sometimes if you skip a rope, then you have a person on either end, and they're skipping it, and you see this like spiral effect, right? And if they do it perfectly in sync on both ends, then it'll be synchronized, and that would be called a sine wave. Everyone knows what that is, right? Sometimes kids on playgrounds will do tricks where they can get two waves. If you've ever seen that, they take really long ropes, and kids might actually skip twice on one rope. Two different kids skipping at the same time. That's creating two sine waves. And the really good ones can do three. I've seen that before. But basically, that kind of wave is what we're talking about. In physics, that kind of wave basically that concept transfers to all of sound and all of light. And even into other things like radiation. But if you were to hear something, then the sound wave typically has a lot of variations of waves that you can't see, but of course they are there. And that's primarily what I'm focused on, is the sound wave in the instrument and how it projects to you, the audience, so that we can get as much of your energy and your effort as a musician into the audience so that you can hear it as well as possible. And that really is what I've focused on since I was about 19 years old. So for about 19 years now, that's all I've done. I feel like one of those people that hasn't accomplished anything because I've been stuck on this one thing. But that's how it goes. And I'll demonstrate and I'll explain how these things work. And of course, you're welcome to ask as many questions as you like. Since it's such a small group, it's a great idea to ask questions because my mind goes in all different directions, and I may miss something that's really obvious. Okay, so does anyone know, let's say you play a C on a trumpet, does anyone know what note comes out of the horn?
B-flat trumpet?
Yeah, it's a B-flat trumpet, and I'm playing open note.
B-flat.
Concert B-flat. Does everyone think concert B-flat, right?
That a trick question?
It's a trick question. I'm sorry, Jim. I didn't mean to get on the spot. There are like 17 notes that come out, believe it or not. If you take an oscilloscope, which is a measuring tool to see which actual partials were present in any sound, then you can see that the overtone series of C should be present. If you're hearing a low C, you should definitely see the fundamental, which is an octave below, and then C itself, and then you'll see the G above that, and the C above that, and it goes E, G, B flat, C. After that, it becomes almost a natural scale. From high C, that overtone is there. You'll hear D, E, F, G, A, kind of an A, kind of a B, and then another C. And it goes on from there, but we don't really pay much attention to anything after triple high C. So all of those notes should be present. However, if you were to measure any trumpet in the whole world, I guarantee you there are other ones that don't belong there that are also present. And the amount of each of these overtones that you hear really determines a few different things. It determines the pitch that you're hearing. It also determines the character or the tone quality of what you're hearing. For instance, if I were to play a C, a low C, and I were to play with a really closed position in my mouth, then you will hear more brightness in the sound, right? Does anyone know why that happens? I'll play real quick so you can hear what I'm talking about. Here's a normal C for me. Now I'll do my best to close my mouth up. Kind of, beginner sound a little bit like that. Why did it sound different? It's the same horn, same player. All I did was raise my tongue and close my mouth as much as possible on the inside when I played the second C. Anyone have any idea why that happens? Well, it's because the resonance of the instrument has changed. So in other words, if you were to map out all those overtones, and I really should have drawn a picture, but I don't have any fancy gadgets to do that today. But if you can imagine, you had a fundamental, which was a C, and then the octave above that is a C that you heard, and then a G and a C and all those overtones, right? When you play with a really closed setting, the lower overtones are less loud, or we call that a lower amplitude. So in other words, you don't hear as much of the lower overtones if the volume of your mouth isn't as large. That's really important to know because when students are learning to play and they want to play with a bigger, broader sound, then a lot of times the only difference between them playing the sound they have and a bigger, more beautiful, full-bodied sound is simply opening their mouths. But to tell a student, say in 5th or 6th grade, you need to open up more, can be really confusing. You don't understand the concept. But that's basically what I'm saying. The more air volume in your mouth, the broader or more amplitude you have in the lower overtones of your sound. Now the other thing is you can change those things in the instrument and in an off-piece, not just in your mouth. So I could build an instrument that sounds brighter or darker in different parts of the overtone series based on your preference. Some people don't like a big full-bodied sound. They really want a piercing double high C sound all the time. And I usually tell them to play a Shoki tuning bell or a Colicchio. But if they really want one of my horns and they want me to build that, I have to do special things to create less air volume throughout the tapers of the instrument. So all of this is kind of the background acoustics to understand the basics of efficiency. And what I mean by efficiency at this very moment is how much energy you put into the instrument and how much of that energy is converted into sound and transmitted to the audience. There are a lot of ways of measuring that. Anymore, I measure it just by picking up horns and playing them. I don't use lots of lab equipment. I don't go crazy with any of that stuff. When I started, I did, and now I don't because after doing it long enough, you can tell if something is projecting or not. There are a few simple tests. You can record it across the room. You can have someone play it or listen across the room. The difference between this horn and a box Stradivarius, hands down, everyone will hear the difference in how far it projects and what kind of overtone series you're going to get on the other end of the horn. So it's that obvious that we can hear the difference, and the efficiency really comes down to how much energy you're putting in and how much people hear on the other end. Now, where would energy go if it didn't transmit into sound? Any guesses? Some of you know the answer. Energy is an interesting thing because the theories behind energy are simple. You can't create energy and you can't destroy it. It can only be transferred. And because you can only transfer energy, then it's all around us in different forms. The energy that you put into an instrument really is the airstream. Some of it is body heat, because you're warmer than the instrument usually. And of course, that creates a buzzing sound when you hold your lips together, which should correlate with the resonating cavity of the instrument, or the length of the instrument. So in theory, if you put the correct airspeed and air volume into an instrument, and you hold your lips the right distance on a brass instrument, you can, by varying that, find the resonating frequency of the length of the instrument. And that complicated mess is how we make a sound on the trumpet.